All right, so in week 4, we're going to dig a little deeper into the multiplication rule for independent events. So I did take my time going over the differences between independent and dependent because you're going to use different formulas for these two. So it's good to kind of really know solidly the difference between independent and dependent. So there's the multiplication rule for independent events. When two events A and B are independent, meaning they don't influence each other, the probability of both occurring is found by this little formula. The probability of A and B, let's make this a little closer here, is equal to the probability of A times the probability of B. Okay, so it's really simple, just straight up multiplication. We love that. When you're looking for the probability of, of A and B. So here's some thoughts about this, or just some examples. Let's say you pull an ace out of a deck of cards, you put it back in and you draw it out again and or draw another card again and you get a spade. Well, if we were looking for those both to happen, and one event happening and the other event happening, we would just multiply the two probabilities together. Same for rolling a die and getting a 4, then rolling a die and getting a 2, because these are independent. You could just multiply those two different probabilities together. Okay, probability of independent events with decimal answers. Of the people who fished at Clearwater Park today, 49 had a fishing license, 21 did not. Of the people who fished at Mountain View Park today, 48 had a license and 32 did not. Note that no one fished at both parks. So just think about two different parks. You've got your Clearwater and you've got your Mountain View. Suppose that one fisher from each park is chosen at random. So one fisher here and one fisher there. What is the probability that the fisher chosen from Clearwater did not have a license and the fisher chosen from Mountain View did have a license? Okay, well, we can use that well, first we need to decide if these are independent or dependent. They're telling us they're independent. Hopefully you're realizing they're independent because the probability of picking a fisher in from this park has no effect on the probability of picking a fisherman from this park here. And so they are independent, which means we can break out our rule, the probability of A and B, because look, they're asking us, what's the probability that the fisher chosen from Clearwater did not have a license? And so that'd be event A, the probability of the fisherman from Clearwater did not have a license. And the fisher chosen from Mountain View did have a license. So we know from that previous slide that we can, with independent events, just multiply the probability of A times the probability of B to get the and. Okay, so let's do some math here. We know that at Clearwater, we have 49 had a fishing license, 21 did not. So 49 had a license, 21 did not. Let's get the total of fishermen, okay? So that's 9, 10, 4, 5, 6, 7. So we have 70 people fishing at Clearwater. So think about those 70 fishermen there. And we know that they're asking that the fishermen chosen from Clearwater did not have a license. Okay, what's the probability that they did not have a license? Did not have a license. Well, that's 21 out of 70. Okay, now that's the probability. We'll call this event A. All right, let's look at event B. So now we're over here at the Mountain View. All right, so they tell us that of the people who fished at Mountain View Park today, 48, so this is Mountain View, 48 have a license and 32 did not. All right, let's add those together. So 8, 9, 10. There's 80 people fishing there. And they're asking us for the probability that the fisherman chosen from Mountain View had a license. So that's 48 out of 80. So the probability that they had a license is having licenses 48 out of 80. Okay, so we have the probability of event A is 21 out of 70. Probability of event B is 48 out of 80. And now we can just multiply them together. I'm going to get a separate piece of paper to have a little bit of room for this. So we're going to keep 21 over 70 times 32 over 80. I'm going to have to break out my calculator. Okay, so I had a little error here. They're asking for the fishermen chosen from Mountain View whether they had a license. So that's 48 out of 80. So it's this one here times this one here. So 2170 times 48 over 80. 21 over 70 is 0.30 and 48 over 80 is 0.60. So let's just think about this for a minute. The first one here is the probability that the fishermen chosen from Clearwater did not have a license. That's 30% chance. This one here is the fisherman chosen from Mountain View had a license. That's a 60% chance. If you multiply 0.30 times 0.60, which we're allowed to do, because remember the probability of A and B is equal to the probability of A times the probability of B, you're going to get 0.18. So this is what they're looking for as far as in Alex, but we could say this to ourselves. There's an 18% chance the fisherman chosen from Clearwater did not have a license, and the fisherman chosen from Mountain View had a license. So hopefully that helps with this type of problem. Okay, let's practice one. So I want you to read this, pause the video, work out the two probabilities, see what you get when you multiply them together, and then check back with me. So if you're back, a spinner has 10 equally sized sections, 4 of which are red, 6 are green. All right, and 4 plus 6 is 10, so that works out nicely for us. The spinner is spun, and at the same time, a fair coin is tossed. Oh, what is the probability that the spinner lands on red and the coin toss is tails? Okay, so we're looking at an and situation that the spinner has to land on red and the coin toss has to be tails. Okay, so probability that the spinner lands on red. Okay, well, we know there's 4 out of 10. Okay, and the probability that you flip a coin and it's tails. Well, we know when you flip a coin, it's 50-50, or 1/2 chance of getting head, 1/2 chance of getting tails. Okay, so because we use the word and, we know the probability of A and B can be calculated by the probability of A times the probability of B. So we have 4/10 times 1/2. Okay, so 4/10 times 1/2. If you want to do this with just fractions, you got 4 times 1 is 4, 10 times 2 is 20, and you reduce that from there, divided by 4, divided by 4. That's 1/5, but they want decimal answers. So do 4 over 10 in your calculator, that should be 0.40, times we know 1/2 in your calculator is 0.50. And if you do 0.40 times 0.50, you're going to get 0.20, or just 0.2, which is 20%. Okay, and the reason we're allowed to do this is these are independent events. Let's keep that in mind. They're independent events because they have no effect on each other. When you spin the spinner and you try to get a red out of the 10 sections, and then you flip a coin and you're trying to get a tails, they have no effect on each other. This here is independent of this event right here. So they are independent, which allows us to break out this handy dandy formula. Okay, here's another one for you to try. Hopefully you got the last one right and you're feeling confident. A student ran out of time on a multiple choice exam and randomly guessed the answers for 2 problems. Each problem had 4 answer choices, A, B, C, D, and only 1 correct answer. What's the probability that she answered neither of the problems correctly? Okay, so think about multiple choice test. Here's question 1, here's question 2. There's 4 choices, and we know only 1 choice is correct. So we know the probability of getting the answer right is really only 1 out of 4 chances. We know the probability of getting it not right, so not correct, is 3 out of 4 chances. Okay, they're asking what's the probability that she answered neither of the problems correctly. This is an independent event because what she answers on question 1 has no effect or does not influence what she's going to answer for number 2. Okay, so that means we can say probability of A and B allows us to multiply the probability of A times the probability of B. Okay, so probability that she gets neither of the problems correct, if she steps up to this problem, getting that not correct or incorrect is a 3/4 chance. That's the probability of A. Then she moves to the next problem, the probability of getting that one incorrect, so they is also 3/4. Okay, so what is the probability that she answered neither of the problems correctly? So this one and that one are incorrect. So event A and event B and are both incorrect. I mean, that would not be good for the student, but it happens. Okay, so we know 3/4 is 0.75 times 0.75, and 0.75 times 0.75 is going to turn to 0.5625. So there's a 56.25% chance that she'll answer this one incorrectly and this one also incorrectly. Problem 1 and problem 2. Okay, moving on. Okay, let's switch over to the multiplication rule for dependent events. Okay, so this is where things get slightly trickier. This can be a bit tricky. How about TRICKY, tricky? Okay, here is the formula. If you have found that you have two events that depend on each other or influence each other, this is how you're going to figure out the probability of A and B both occurring. You're going to multiply the probability of A times the probability of B, and here's the caveat, given that A has already occurred. This is where things get a little stinky, okay? So we're going to go slowly through this so that you feel good when we get done. So here's some examples. Let's say you pull an ace out of a deck of cards, and then you throw it away. Or you burn it. And then you draw again and you get another ace. Well, this second event is definitely dependent upon you taking that ace out and throwing it away. It's going to be different. There'll be 52 cards when you step up for this event and only 51 cards when you step up and pull out for this event. Or you pull a red ball out of the bag, out of this bag. Let's say you take this red ball, you pull it out, it's gone. And then you come again and get a blue one, okay? So we know that they're going to influence each other. So you can even look to see, like the probability of getting a red ball is 1, 2, 3, 4, 5, 6, 7, 3 out of 7. But if you take this ball out, the probability of getting a blue now is 1, 2, 3, 4 out of 1, 2, 3, 4, 5, 6 now. So see how those denominators change. So with the removal of that red marble or whatever that is out of this bag is going to cause the denominator to change in event B. So this is influenced by what happened with event A. Okay, probability of, this should say dependent events. Okay, Parcell's hint. When you see the word given, every time your denominator, or sometimes I call it your bikini bottom, will change. Arg matey. So just keep that in mind. When you see the word given, you're going to have a change of bikini bottom or denominator.